Well, hello friends, welcome to this video. In this video we will be discussing regarding, or rather continuing the discussion on fidelity and trace distance. So we have already started the discussion and we have almost ended it. So this video will be like summarizing all the discussions of fidelity and the trace distances. So we saw that the trace distance between two states or two density matrices are given in this form. And then further we saw that the trace distance can also be characterized using maximizing over all the projection or the projection operators and then taking the trace. So these have been discussed in the videos provided in this series that we are discussing on. The second point is that the fidelity is shown in this form. This is the definition of the fidelity, and it is somehow related to the angle between the states over the Bloch sphere, which we have discussed in the video under fidelity, the previous one. And it can also further be quantified over in the form of two pure states. So these are the pure states. So here you see the density matrices, they need not be the pure states. But here this is the purification of this density matrix. So this is the purification of this one, this is the purification of this one. And then we said that it is the maximum, it is such purification, it is such a purification that maximizes this entire norm. And then further we saw that this norm and fidelity are connected to something that can be constructed to a actual metric over the space of these density matrices. So now, and also we saw that when we have two states, and when we trace out the system, the states are supposed to become less distinguishable. Like, because tracing out is inherently associated with some sort of an information loss. So it makes sense to say that the tracing out makes the states come closer, or they make them more less distinguishable. So here you can see that as per the trace distance, we see that if we have completely indistinguishable systems, that is sigma equal to rho, we should have d equal to 0. But in case of fidelity, completely indistinguishable systems will have so you put rho here, so that will become rho, and trace of a density matrix is 1 by the normalization. So fidelity of completely indistinguishable system is supposed to be 1. Similarly, the A can be found out because cos inverse of 1 is 0. So this means that when we trace out a system, and in more general sense, when we perform some sort of a quantum operation, in terms of the trace distance, we are actually reducing the trace distance, because the most indistinguishable case has a trace distance of 0, and when we are actually performing a quantum operation, we are making our states more indistinguishable, and the most indistinguishable case is 0. So this is the sign for the trace distance. But you see, the sign for fidelity is actually just the opposite. This is simply because of the definition of fidelity that we have already discussed. So these are the three inequalities that must be remembered, and intuitively if we remember just the formula of fidelity and trace distances, these are easy to see. Now we will be proving one of the important inequalities associated with fidelity and trace distance. So consider two states. So when we have two states, we can separate the orthogonal parts of the states, and without any loss of generality, one of the states can be named to be 0, and apparently you can remove the 0 part from the other state and you can name the other part as 1. So these are the two states. And if we remember the Bloch sphere, so in the Bloch sphere representation, these two states are supposed to be denoted like this form. So the state 0 lies in the top of the Bloch sphere here, and the state B, which is cos theta by 2, is actually making an angle of theta. So this is an important point. It is related to the important point of Bloch sphere, and it is related to fiber bundles and all those things. And so this point here is actually the point B, although the angle is theta by 2, but actually the angle is theta because the 2 to 1 correspondence between SO3 group and SU2. Okay, so after that, after we have classified this entire thing, so our Bloch vectors are 0, 0, 1, which is this point here, and other point is this point. This particular thing we can recognize that it is just the actual point here. The point here will be what? It will have a z component of cos theta, and it will have a x and y component like sin theta cos phi and sin theta sin phi. Now given these A and B, this states that we see here, we can construct the density matrices corresponding to these states. And how we will do that? We will just write A, and similarly we will write B and B. So when we do that, we see the trace distance. This formula has also been discussed. The trace distance in case of a Bloch sphere reduces to a proportionality to the actual radial distances. So you see, this is the magnitude. This is just the way we find the Euclidean distance. So the trace distance is just the Euclidean distance between the Bloch vectors, and that is found out to be norm of sin theta by 2. So this is for two pure states. A and B are pure states. So by definition, because you see the A and B are pure, because the rho is A times A, like this. Now let's move on. Similarly, we can find the fidelity. Fidelity of two states which are pure is simply the overlap, and we get cos theta by 2. So we see that for pure states, the fidelity, fidelity and trace distance is related by this form. So this form is only valid for the pure states. But for impure states, or at least one of the two states, when they become impure, we have to use these formulas. So when we do that, so we see that given you have pure states rho and phi, which are the purification of you have the states psi and phi, and it is the purification of rho and sigma. This inequality will always hold because of exactly this point, because purifications are associated with tracing out our systems. So as this inequality holds, and on the other hand, for the fidelity case, this purification of the state, if it is maximized, this is actually an inequality. This is no longer an inequality. So for fidelity case, this is an equality. For trace distance, this is an inequality. For fidelity case, it is an equality because of this form. We have chosen maxima. So when we do this, so we see that d of rho sigma is less than equal to d of psi and phi, which is the purifications of rho and sigma, which is in turn equal to this. So why is this equality true? Because we have just proved that for pure states we have this equality here. So, and hence this is the final result. So it says that d of rho sigma is always less than equal to under root 1 over f square of rho sigma. So let me write the final result. d of rho sigma is always less than equal to under root 1 minus f square of rho sigma. So this is what we managed to show. So with this, the discussion on fidelity topic will be put on to an end, and we will start with the discussions on entropy. So entropy or information content. So we will be discussing on information theory. And while doing so, we will be actually starting with something called as Rayleigh entropy, which is a sequence of entropies ordered by a parameter. And these are important because, first of all, we see the thermodynamics. As we know, the entropy of thermodynamics is only defined in case of equilibrium systems, and we often associate this with the disorder content. But when we have systems which are not in equilibrium, so the non-equilibrium or strongly correlated systems, then we have to use a different procedure to understand what the very notion of entropy means. So for this, we will see that actually the information theoretic notion of entropy comes to be very handy, and it is what actually leads finally to the laws of quantum thermodynamics. So that's all for this video. In the next video, we will discuss on these topics. Thank you.